Welcome to EFSA's E-learning on uncertainty analysis. I'm Andy Hart, and this is the first of 3 presentations in the course. In this presentation, we introduce EFSA's guidance on uncertainty analysis and look at an example from animal health. In EFSA's guidance, uncertainty is used as a general term referring to all types of limitations in available knowledge that affect the range and probability of possible answers to an assessment question. This includes limitations in the relevance, reliability and consistency of evidence used in the assessment, which might include data, statistical estimates, modelling, qualitative evidence and expert judgment. These things are always uncertain to some degree, and they matter because they lead to uncertainty in the answers to assessment questions. So, when is uncertainty analysis required? EFSA Scientific Committee has said all EFSA scientific assessments must include consideration of uncertainty. Specifically, assessments must say what sources of uncertainty have been identified and characterize their overall impact on the assessment conclusions. This is necessary because the uncertainty of scientific conclusions has important implications for decision-making. Risk management decisions should take account of the range and probability of possible outcomes, not just the best estimate. Risk managers may need some support and training on this. In addition, characterizing scientific uncertainty is important for the transparency of EFSA's work. Of course, scientific experts are used to dealing with uncertainty. Here are some approaches we commonly use. However, all of these are subject to important limitations. Confidence intervals quantify the range and probability of values, but include only uncertainty due to sampling variation, which is often a small fraction of the total. Sensitivity analysis is an excellent way of exploring the potential impact of alternative estimates and assumptions in a quantitative assessment, but generally provides information only on the range of possible answers and not their probability. Conservative assumptions and scenarios are designed to ensure our assessment is on the safe side, but don't tell us how likely that is. And verbal qualifiers in conclusions, including words such as likely, suggest, or cannot exclude, indicate the presence of uncertainty but are highly ambiguous about the range and probability of possible answers. So what do we need to do? We need to systematically identify uncertainties affecting each assessment, assess their combined impact on the conclusions, in other words, the overall uncertainty, and express this as the range of possible answers and how likely they are. EFSA's guidance on uncertainty analysis provides the methods for this. The guidance is supported by a much longer and more detailed opinion on the principles and methods for uncertainty analysis and by a separate guidance document on communication of uncertainty in scientific assessments. In addition, uncertainty checklists of 2 or 3 pages have been developed as a quick reference guide for use in particular panels or particular types of assessment. The guidance on uncertainty analysis contains flowcharts providing step-by-step guidance for 4 different types of assessment. The most common types are standardized assessments and case-specific assessments. Standardized assessments are common for regulated chemicals with standard data requirements and standardized assessment procedures. Case-specific assessments don't use a fixed procedure. Rather, they use approaches chosen by the assessors to suit the assessment question and the data available to answer it. This applies to nearly all EFSA assessments outside the chemical risk area, and also to chemical assessments where non-standard data or procedures are involved. Less common situations are urgent assessments with an unusually short deadline, e.g. days or weeks, and development of or revision of the procedures used in standardized assessments. This is likely to be needed when you are developing a new guidance document or revising an existing one. This course focuses on case-specific assessments. Section 4 of the guidance provides 6 flowcharts covering different options for uncertainty analysis in case-specific assessments. The uncertainty checklists condense this into a list of steps. Basic steps that are needed in every case-specific assessment, and additional steps for optional use when a more refined uncertainty analysis is needed. This presentation and the next one focus on the basic steps illustrated by examples from animal health and biohazards. We'll look at the additional steps in the third presentation illustrated by an example from plant health. So what are the basic steps that are needed in every case-specific assessment? Ensure assessment questions are well defined. Include uncertainty analysis when planning the assessment. Identify sources of uncertainty while doing the assessment. Ensure draft conclusions are well defined. Assess overall uncertainty for each conclusion, and report the methods and results appropriately. What makes this basic is that the combined impact of all the uncertainties is quantified in a single step, whereas in a refined assessment, some sources of uncertainty are quantified separately first. Let's look at an example of a case-specific assessment using just the basic steps of uncertainty analysis. The example is from an EFSA opinion on African swine fever published in 2019. The first of the basic steps is to ensure the assessment questions are well defined. The terms of reference for the assessment were to estimate the risk of spread of African swine fever in the southeastern countries of Europe. The terms of reference did not define spread or southeastern countries, so the panel defined these terms in their interpretation of the terms of reference. They defined spread as propagation of the disease within a year, and they defined southeastern countries by listing countries in what they called the region of concern, or ROC. The second step is to include uncertainty analysis when planning the assessment. In this example, the approach taken was to define a set of indicators that could favour spread of the disease, review the available evidence, and then use the evidence to assess the indicators for each country and assess the probability of spread by expert judgment, taking account of the evidence and uncertainty involved. The third step is to identify sources of uncertainty while doing the assessment. The panel summarised their assessment of the indicators in tables. They identified uncertainties due to missing data for some countries, uncertainty due to the variation of indicators between countries, and uncertainty about the contribution of different indicators to the risk of spread. The fourth step is to ensure draft conclusions are well defined. The panel drafted its conclusion in this form: the probability that African swine fever will spread within the region of concern within 1 year of introduction is, and then added their assessment of the probability. This wording defines the outcome of interest, the geographical region, and the time period. The fifth and key step is to assess overall uncertainty for each conclusion. If the disease does enter the region of concern, then either it will spread within a year or it will not. So the probability assessed by the panel expresses their uncertainty about whether spread will occur. The panel assessed this by expert judgment using a scale of approximate probabilities. They concluded that the probability of spread within 1 year of introduction is very high, between 66 and 100%. This was a consensus judgment of the working group, based on the evidence and uncertainties involved. The panel summarised the rationale for their judgment, including the high number of indicators present in most of the countries in the region of concern, and the known effect that these can have on spread, especially indicators related to the percentage of smallholder farms and the risk of poverty, and indicators related to movement of people between countries. The swine fever example uses probability to quantify uncertainty. The guidance recommends that assessors should always try to quantify the overall uncertainty of assessment conclusions using probability. The guidance expresses probability as a percentage between 0 and 100%, where 100% means the event in question is certain to occur. For example, the conclusion is certain to be correct. And 0% means the event in question is certain not to occur. The guidance recommends using probabilities because they have defined meaning, which other methods of expressing uncertainty lack. For example, if we say a conclusion has a probability of 50%, we mean it is as likely as tossing a coin and getting heads. More probabilities, from 1 chance in 6 to 5 chances in 6, can be defined by comparison to rolling dice. And any probability can be defined by comparison to taking coloured balls from a jar or a bag. For example, 90% probability means as likely as drawing a red ball from a jar containing 9 red balls and 1 black one. So EFSA recommends using probability because it has defined meaning, whereas qualitative expressions of uncertainty or confidence are ambiguous and interpreted differently by different people. A massive variety of words is used to express uncertainty in everyday language, but almost all of them are ambiguous. For example, if you ask a group of people what probability they associate with the word likely, you will normally get responses ranging from around 50% up to over 90%. In the study shown here, it was a group of plant health risk assessors. This has 2 serious implications for risk assessment. First, it means that when doing an assessment, a group of experts may agree a conclusion is likely, when in reality they have quite different opinions. Expressing their judgments using probability reveals the differences so that they can discuss them and arrive at a better consensus. Second, if the experts report a conclusion as likely, the risk manager's interpretation of this may differ markedly from what the experts intended, which could have an impact on risk management decisions. In the swine fever example, the probability was assessed by expert judgment. Of course, it's good to estimate probabilities from data when suitable data are available. However, overall uncertainty must always be assessed by expert judgment, because there are always some uncertainties that cannot be quantified from data. Expressing overall uncertainty qualitatively does not avoid the expert judgment, it just makes it ambiguous. Of course, expert judgments must be based on evidence and reasoning, which should be documented, and expert judgments are subjective and affected by psychological biases. So for these reasons, EFSA guidance provides structured methods for probability judgments that ensure they are based on evidence and reasoning and guard against biases. We'll look more closely at those methods in the next presentation. So when is quantification possible? The uncertainty guidance recommends that assessors should always try to quantify overall uncertainty using probability. This should usually be possible because EFSA conclusions should be well-defined scientific statements, And, in principle, it should always be possible to express uncertainty about a well-defined statement using probability. Clearly, EFSA should only report conclusions to risk managers if the assessors judge they have some probability of being correct. They should at least be able to rule out that the probability is zero and say where their probability is more likely to lie. This applies to all types of EFSA assessments, both qualitative and quantitative. If assessors are unable to give even an approximate probability for a conclusion, this implies that the probability could be anywhere between 0 and 100%. So they should report that the probability of the conclusion is unknown, or report it as a hypothesis, and avoid any verbal expression of likelihood or confidence, because that would be misleading. The guidance recognises that in some areas of EFSA's work, especially regulatory assessments, legislation or risk managers may require firm conclusions without probabilities. However, it is still beneficial to use probabilities when conducting those assessments, even if they are not included when reporting the conclusions. This can be done by defining what level of certainty, i.e. probability, is required for each type of conclusion. For example, if a firm conclusion had been required in the swine fever opinion, the assessors could have defined an upper level of probability that would justify reporting spread is expected, and a low level of probability that would justify reporting spread is not expected, with intermediate probabilities being reported as inconclusive. Probability thresholds of this type should be agreed with risk managers because they require risk management judgments, and they should be published if possible for transparency. Once the thresholds are defined, the panel can quantify uncertainty in terms of probability when conducting the assessment, but translate this into appropriate verbal conclusions for reporting. In this presentation, we have introduced key concepts and principles for uncertainty analysis. We've looked at a basic example on African swine fever and explained why EFSA's guidance recommends using probability to quantify overall uncertainty. In the next presentation, we look in more detail at the methods and options for basic uncertainty analysis using an example from a different area of EFSA's work.